This week we turn toward quantum statistical mechanics. So I think I used the phrase we snuck quantum mechanics in a few times, in the sense that we used discrete systems that we had already considered before in quantum mechanics, hopefully. Hopefully you'd seen harmonic oscillator before, rotations of a molecule, but maybe less likely, but still things that we sort of can solve in quantum mechanics and then just bring the energy spectrum over and treat it as a discrete system in classical statistical mechanics. Where we're going is to sort of systems where you can't ignore the quantum nature of the system. So today's lecture, we're going to look at the ideal gas, but from a quantum mechanical perspective, where instead of saying we have a continuum of positions and a continuum of momenta, we take account of the fact that if we have a box with a gas trapped inside, you have a fixed discrete spectrum. The spacings between those levels are extremely small compared to the energy scales we normally think about, even if we're thinking about a gas molecule at room temperature. The energy scales of the box are going to be much, much smaller than that, so we can treat it effectively like a continuum, which we've done before. But today we'll be careful about the fact that this is really also a discretized system that looks like a continuum at high temperatures. Then in the next lecture on Wednesday, we're going to talk about systems where interference effects between particles become too big to ignore. And in some sense, this is the real transition into quantum statistical mechanics. So today's lecture is sort of like hydrogen, like the Bohr model for hydrogen, right? It works, but it's sort of a semi-classical thing, because for the particular case of an ideal gas, as long as the temperature is relatively high and anything we encounter in everyday life is quite high by the standard we're going to talk about, then we can treat it basically as a classical gas or as a classical system statistical mechanically. But you'll see Planck's constant pops up. And before, we could have just treated this like a continuum and at the end said, hey, Z should be unitless, and it's not. What's the unit? Oh, gee, it looks like h cubed. Just throw an h cubed in. That's an argument that you can make. Here we're going to really see, if we respect quantum mechanics from the beginning, how we get the partition function that we would expect. In the next lecture, this is more like helium, okay? So the Bohr model works for hydrogen, actually works quite well. You can even do perturbations on it and fix things up. But with helium, you have two electrons. And the anti-symmetrization of the electron wave function creates a system that you just can't possibly describe with a semi-classical model like the Bohr model. In fact, so the failure with helium is in some sense the reason people knew they had to go push further than just something like a Bohr model. So similarly, as soon as we start talking about places where interference, and by interference I'm using that as like a catch-all term for different things, but in particular, effects due to symmetrization and anti-symmetrization of wave functions, when those effects become important, then the statistical mechanics of the system becomes fundamentally quantum mechanical. There's no way to ignore it at all. So that's the sequence. First, we'll look at discretizing the continuum in terms of wave functions, and then next lecture we'll start talking about these interference effects. Today we'll get a sense of when those interference effects should become important. Next lecture we'll learn how to deal with them once they are important. So we'll start by considering a gas trapped in a box. And as we've done anytime we're thinking, in this lecture we're back to the canonical ensemble, I should say. We talked about chemical potential in the last lecture. It's going to be important in the next lecture for dealing with these cases where interference becomes important. But for now, we're going to talk about the ideal gas, and we're going to be back in the canonical ensemble for this. So anytime we've talked about the canonical ensemble, we're generally thinking about the partition function for a single particle or single small system. And then we learned several lectures ago that if you have a bunch of identical independent systems of that type, then you can just take the product of the partition function for all of them. So that's going to be our strategy here. We start by looking at what happens with a single gas particle. And I should say, I'm going to say particle because some of these considerations look at the internal structure of the particle, but many times we're not going to care about the internal structure. We're going to sort of factor that part out. Okay, so to start with just thinking in one dimension, the position variable for a particle. If it's a gas in a box, then our potential has sort of infinitely high walls in two places, and the potential is 0 everywhere in between. So our x-coordinate and our energy coordinate, this is the length of our 1D box. And again, you should have seen this already in quantum mechanics. The wave functions that fit in this box are wave functions that go to 0 at the boundaries, right? These hard walls give you a boundary condition. The wave function has to go exactly to 0 at the edges. And so just like when you ask the question, what standing wave modes can I fit on a string that's got hard boundaries at the edges, right? Violin, guitar, piano, whatever your favorite instrument is, you can fit a half wavelength on the string. You can fit a full wavelength on the string, right? 3/2 of a wavelength. As long as you have integer multiples of a half wavelength, they'll fit with the boundary conditions. So that's what happens with the wave function here. And when we solve for the energy, we find, this wavelength is 2L, right? And so using the fact that wavelength and momentum are inverses of one another, right? That 1 over 2L is equal to h over p. 2L. I'm inverting things already. 2L is equal to h over p, right? And p squared over 2m. We put those two facts together, and this gives us our energy, which is h squared over 8ml squared. And so importantly, energy goes like momentum squared. If the momentum looks like 1 over the wavelength, then as we fit more and more wavelengths into the box, our wavelength's getting shorter, which means our momentum's getting higher, and it's going to go quadratically because it's a momentum, right? So we have this sort of fundamental number for the ground mode, and then now we fit twice as much of a wave in here. That means the wavelength is half squared, right? 1 over a half squared is 4. So our energy is 4 times h squared over 8ml squared. We fit 3 half waves in here. That's going to make us 9 times higher than the ground, and so forth. So the general formula is just n squared h squared over 8ml squared. And that's the spectrum of the infinite square well. It's what you probably called it in quantum mechanics. Let's just say a box. Okay. The spectrum of our box looks like this. Keep in mind this is a one-dimensional box. When we want to go to 3 dimensions, we're just going to say this dimension, this dimension, this dimension. They don't talk to each other, so we can just take their product, and that will be the spectrum. Or rather, the sum here. Good. So if we wanted to think about how does this look for an oxygen molecule in a 1 centimeter space, well, we can just plug these numbers in, right? Our fundamental unit is this h squared over 8ml squared. What is that for an oxygen molecule? So Planck's constant, 8. An oxygen molecule is 2 oxygen atoms, which is 16 atomic mass units each for a total of 32. That's the atomic mass unit in kilograms. And then L is a centimeter, so 10 to the minus 2 meters squared. Churn through it, 1.7 times 10 to the minus 38 joules. That's an extremely small amount of energy. And to get a better grip on exactly how small it is, let's compare it to something. Let's compare this to KT at, room temperature. I always use 300 Kelvin, even though I don't keep my room quite that hot, right? 295 is probably closer to room temperature, but warm room temperature. It's all about the same, right? Because it's a multiplicative scale. 295 versus 300, we'd end up with the same answer over here. So Boltzmann's constant, 1.38 times 10 to the minus 23 joules per Kelvin, 300 kelvins. So at room temperature, KT is 10 to the minus 21. I mean, we hardly care about the 4 out front. It's there, don't forget about it, but 4 times 10 to the minus 21, essentially 2 times 10 to the minus 38. This is 16, 17 orders of magnitude in difference between these energies. Now, since our energies go like n squared times this number, right? If we just take the ratio of h squared over 8ml squared and kT, we can see that the energy that corresponds to kT at room temperature gives an n of 500 million. Okay. So for an atom or a molecule at room temperature, you have something like 500 million states accessible, if you think of sort of kT as setting your energy scale. It's a lot of states, and so we are not going to notice the difference between one or the other state, right? If it's state number 499,900,001, right, versus 499,900,000, or even subtract 3 from that, you're not going to notice these differences. And this is why, at the end of the day, we can treat this whole thing like a continuum and get answers that are very good. So to quantify this in a different way, suppose instead of saying 1 centimeter, done the metric 1 centimeter, I do know the metric system even though I'm from the US, because we use the metric system in the lab. Okay, so instead of just a centimeter spacing in 1D, let's say it's a cubic centimeter of oxygen. At standard temperature and pressure, this would be, well, this isn't quite standard temperature. Standard temperature is 273 Kelvin. I did the math in the background, and I also used a very, very approximately sign, so all is forgiven. So at standard temperature and pressure, I know 22... I know that n can be 500 million in each of my 3 directions. So I'm going to cube that. And that tells me I have about 10 to the 26 states available. And now I was getting ahead of myself because I was so excited to use high school chemistry knowledge, right? How many molecules do we have? That's why I picked standard temperature and pressure, because I remember that this is 22.4 liters for a mole. So Na is Avogadro's number. And this is a milliliter, so 22,400 is what we're dividing Avogadro's number by. So our number of molecules in this cubic centimeter, when I don't look at my fingers, I do the right size. In the cubic centimeter, we get 3 times 10 to the 19 molecules. Or if I take the ratio of the number of states and the number of molecules, we have about 3 times 10 to the minus 7 molecules per state. Okay. So this is important for what I mentioned at the beginning of lecture, this sort of idea that interference between particles is what we're going to look at in the next lecture. That's when quantum mechanics becomes unavoidable. At room temperature, or standard temperature and pressure, the number of molecules per state is so low that the odds of 2 molecules trying to occupy the same state is vanishing. Okay. We're not going to worry about these interference effects or effects that arise from symmetrization, anti-symmetrization of the wave function, because anti-symmetrization and symmetrization become most important when 2 things try to be in the same state. And of course, the odds here that 2 molecules want to be in the same state, I'd say it's 1 in a million, but that's actually giving it a little too much credit. Right? It's 1 in 3 million. Okay, so this is why we're going to get away with ignoring interference effects now. Next lecture, we want to talk about interference effects. You can see I keep looking ahead to next lecture because quantum statistical mechanics is where things, to me, get even more exciting than they've already been. Also, it's kind of what I do for a living. So that's that's also good. All right, so we've talked about the spectrum. If we know the spectrum, we can calculate the partition function. I'm just going to drop back to 1D for the same reason that I did before, namely, we can treat all 3 dimensions of space as independent and then just take a product at the end. So in 1 dimension, we've just got our partition function as a sum on exponentials, e to the minus beta energy, right? N equals 1 through infinity. I'm going to now approximate this as an integral. And hopefully that doesn't give you guys nightmares after problem set 2. Maybe it gets you thinking a bit here. Is this a good approximation? Is this the right way to approximate this integral? Or this sum, sorry. Is this integral the right way to approximate this sum? I'll let you think about it a bit. Maybe discuss it in Piazza. Nonetheless, it's the way we're going to approximate it for now. The best part about using this integral to approximate it is we can do this integral, okay? We could pick some other integrals that we can't do. So we're just taking this across. We're approximating this. Yeah, okay, I'm going to say it out loud. There's a 0 at the lower limit here. There's a 1 at the lower limit here. I know in my heart it doesn't really matter for the cases that we're looking at, but think about how we're approximating this as an integral. But again, it's an integral that we can do, so great, let's do it. This is just a Gaussian integral. And in this integral, what is sigma squared? Well, again, the form is 1 over 2 sigma squared times our x squared, or in this case, our n squared. So everything but the n squared, this stuff, set that equal to 1 over 2 sigma squared and solve for sigma squared. This is what you get. So that's our sigma squared, and then we know the Gaussian integral is just square root of 2 pi sigma squared. And of course, that's for the Gaussian integral from minus infinity to infinity. We can do this integral because the Gaussian is an even function, and so the integral from 0 to infinity will just be half of the integral from minus infinity to infinity. Okay. So we can do this integral. I'm going to pull the L squared out now. It's just an L. And what's left inside is this really great quantity. We're going to spend a whole section of the lecture talking about it. I've given it the symbol lambda t, which is not what Schroeder calls it. In fact, all right, I'll tell you what Schroeder calls it. Schroeder calls this thing the quantum length. And somehow calling it the quantum length sounds very spooky to me. And it's not spooky. There's a very elegant interpretation of this quantity. This quantity comes up quite a lot. That's why it gets a special name. So this lambda t, I told you what Schroeder calls it. Lambda t here is standing for the thermal wavelength, or more completely, the thermal de Broglie wavelength. So this is somehow related to the de Broglie wavelength of the particles in the gas, and we'll talk about exactly how it relates in the next section. Okay, so the thermal de Broglie wavelength. I've rewritten it to be a bit clearer here, right? So this is h over the square root of 2 pi mkt. Okay. So how does this work? And I realize now I did actually have the way Schroeder wrote it in my notes, just not right up at the top there. So remember that the de Broglie wavelength, lambda dB, for a particle is Planck's constant over the momentum, or h over mv. Right? This, of course, is more general. There was a bit of a discussion in Piazza about momentum versus velocity, and momentum is sort of the better variable in the sense that it's the natural variable when you're talking about relativistic things, but we're not looking at relativistic gases now. So h over mv, good. Now, if we have a gas with a distribution of v's, we might ask a question like, what's the average de Broglie wavelength in the gas, right? Planck's constant and m, these are not going to change, so h over m times the average of v inverse. And we know how to calculate averages of powers of the speed, Okay. We've got our good Maxwell-Boltzmann distribution from a few lectures back. Just pull it over. So that was 4 pi m over 2 pi kt. This already, this has a bit of a hint of this de Broglie wavelength already sitting in there, just in the normalization factor. Good. Integral from 0 to infinity, dV, right? So normally the Maxwell-Boltzmann distribution would have a v squared here. We're calculating the average of 1 over v, so this is v squared over v gives us just 1v, which is great. This is just crying out for a u substitution, right? The derivative of this exponent, I'm going to ignore the minus sign because I want that there in the end. So the derivative of everything else here is just beta mv, right? So we just need to multiply this guy by beta m, which puts a 1 over beta m out front. And now we're just integrating 0 to infinity e to the minus u. You know this integral, this is just 1. Good. And now a whole bunch of things cancel out here. So when the dust settles, the h is unharmed. Okay. This is like a 2 pi and a 2. The 2 survives. The 2 pi cancels out some of the 2 pi's down here. Beta and m here cancel out some betas and m's here. And we end up with this expression, which, if you look up here, beta just brings a kt down to the bottom. And we've got h over square root of 2 pi m kt. Right, so this is the lambda t, the thermal de Broglie wavelength that we defined before, and there's just a factor of 2 out front. So the average wavelength in the gas is twice the thermal de Broglie wavelength. Now, why didn't we name the thing with the 2 in it? The important thing here is, two important things. One, I've probably got my face over the equation, so let me just say again, right? This we've calculated 2 times the thermal de Broglie wavelength, because if you compare this guy up to here, you see you've got the de Broglie wavelength, thermal de Broglie wavelength. Now, if we picture a particle and it's got some wavelength, okay, drawing this guy in orange, there's one cycle of the wave. Got another particle with the same wavelength, or close enough that we don't care that it's not the same wavelength, similar wavelength. Okay, draw this guy here, another full cycle of the wave. The point at which this one's peak and this one's trough overlap, this is sort of the last point at which these are very distinguishable. Right? If I go to half this separation, they're going to overlap very strongly. And so there's no chance that you can treat them as independent anymore. Another way to say this is the thermal de Broglie wavelength is the inner particle spacing that means interference is going to become unavoidable. Okay. So this is important as we move into quantum statistical mechanics. This will be a metric for, are our particles too close together to ignore the symmetrization and anti-symmetrization of the wave function? So this is why this is such a key quantity, this thermal de Broglie wavelength. Okay, it sets, another way to say this is, it sets sort of the length over which you expect coherence in the gas. If the thermal de Broglie wavelength is like so, and the inner particle spacing is like so, then you don't expect any coherent effects. Okay, so coherence is just another way of saying interference effects between the particles. Okay, so that's our thermal de Broglie wavelength. This is what it's really telling us physically in the gas. And as we saw before, the thermal de Broglie wavelength at room temperature is going to be much smaller than the spacings between the particles. Okay. We'll quantify that in a second. So let's just look back again. Our one-dimensional partition function was just L over lambda t. If we have many particles, so L over lambda t is going to be an important quantity. Sorry, let me just say that part. Okay, it's implicit, but this is going to be important. This is sort of the ratio of how much room we've got to how many sort of distinct boxes we can put particles in before things get too crazy. Okay. if we flip this over, it's the opposite, right? It's how many, we've got the size of the little box that we can distinguish them in over the total length. So 1 over our number of boxes. If we then multiply by the number, that's going to tell us the number of particles per available box. Okay. And if that is much less than 1, that's the situation we talked about before where we have far fewer molecules than states. Okay. So that's in 1D. In 3D, all we're going to do is cube the thermal de Broglie wavelength. So instead of a 1D box of coherence, we've got a 3D box of coherence, right? We've got like a coherence volume, and we're going to cube the L, right? Instead of having a length of our box, we have a volume of our box. So in 3 dimensions, this sort of average occupation just looks like n lambda thermal de Broglie wavelength cubed over V. N over V is just the number density, little n. Number density times the size of our coherence box. This is an important quantity called the phase space density. Okay. I feel like I should also point out now, my notation is diverging from Schroeder's here, right? In fact, I told you already, he calls this thing the quantum length. And lambda thermal cubed, right? Thermal de Broglie wavelength cubed is something that he calls the quantum volume. Okay. Again, coherence volume would be a much better term from where I'm sitting. But at the end of the day, I think thermal de Broglie wavelength is the most used term in the literature. And phase space density here is a very important quantity. There's not 100% agreement on what people call that in the literature, but D comes up more often than anything else, so we'll call it D. Okay. So D here is our phase space density. And now you may have heard this phase space term in 358. You also may have heard it in classical mechanics. Okay. So phase space, this is this sort of abstract space that includes both position and momentum. Okay. So if you've taken classical mechanics, you probably talked about the fact that phase space is the natural place to describe dynamics. In particular, the Hamiltonian description of classical mechanics takes place in phase space. So your variables are not just x, it's x and p. So the phase space density is the number of particles divided by the volume in phase space. And now the way that we think about that is thermal de Broglie wavelength is 1 over a momentum, right? So we think of 1 over the thermal de Broglie wavelength as a distance in momentum space. So the thermal de Broglie wavelength cubed is like 1 over a volume in momentum space. So the phase space density D is the number of particles divided by the volume divided by the volume in momentum space. Okay, so that's how I've written this. The number divided by the volume in x space or position space divided by the volume in momentum space. So you've got your number of particles per phase space volume. That's the phase space density. Okay. Now, how do we use this? Well, if we're talking about a room temperature gas, let's do this. And now I've gone to 273 Kelvin because I'm going to compare this to the STP calculation from earlier. Let's go ahead and use the proper temperature for standard temperature and pressure. Okay. So the thermal de Broglie wavelength, h over square root of 2 pi mkt. Just plug in the values, right? H, 2 pi, you remember the mass, Boltzmann's constant again, and the temperature. Churn through it. Here's what you get. So you get essentially 2 times 10 to the minus 11 meters. This is interesting because this wavelength is actually much smaller than like the physical size of an oxygen molecule. So when you, an atom, right, a hydrogen atom, what's the size of a hydrogen atom? This is something that you should have in your head for reference. The size of a hydrogen atom is set by the Bohr radius. And the Bohr radius is 5 times 10 to the minus 11 meters. So this thermal de Broglie wavelength is smaller than a hydrogen atom. Oxygen is a much bigger atom than hydrogen. And an oxygen molecule, you've got the length of the bond in there too. This is like an order of magnitude smaller than the physical extent of the oxygen molecule. So you can pretty well guess that this is not going to be an important length scale. Again, at 273 Kelvin, 0 Celsius, or as we're calling it recently in Waterloo, super warm. It's been very cold lately. Okay, so that's our thermal de Broglie wavelength. What's the phase space density? Well, N, we already talked about the number of molecules in a cubic centimeter of oxygen at STP. Plug in the thermal de Broglie wavelength cubed, right? Our phase space density is N thermal de Broglie wavelength cubed over V. So here's N thermal de Broglie wavelength cubed over V. And we get a phase space density of 2 times 10 to the minus 7. Given that I was super sloppy up above, so very schematic in the calculation, this 2 times 10 to the minus 7 is essentially, oh, where was it? It was so long ago. It's essentially the same as what we got up here. We got 3 times 10 to the minus 7, but again, there's a bunch of these squiggly approximation signs. The point that I want you to see is this phase space density is telling us the same thing that we calculated way up there, where we said, look at the individual states that can fit into the box. How many molecules do we have per state? This phase space density is answering exactly the same question. So that volume in position space times the volume in momentum space, that's really getting at the number of little boxes in phase space that we have available, and then we're dividing the number by the number of particles by the number of little boxes in phase space that we have available. So now that we've talked about sort of all the concepts going into this, just want to run through some calculations quickly. So there, at various times in the book, Schroeder has given you the partition function for an ideal gas, or in last lecture, I gave you the chemical potential for an ideal gas. Okay. But now you've earned it, right? Now we've seen, starting from the spectrum of a particle in a box, we can pull all the way through to the partition function for an ideal gas. And from there, we can calculate sort of any quantity of interest for the bulk properties of the gas. So let's do that. But first, I need to be a little more careful about the partition function. I've left something out. I talked about oxygen O2 molecule, right? That's got vibrations, that's got rotations. And so far, we've completely ignored that. But what I want to tell you is that's fine, okay? Because the translational degrees of freedom and the internal degrees of freedom are decoupled from each other. And we've seen several examples of this where we say, like, let's say I've got 2 particles. In principle, what I should do is calculate the sum over all possible states of the 2-particle system, and it's e to the minus beta energy of the 2-particle system, right? Sum that up. That would give me my partition function. But we've seen that, in fact, as long as the energies are not related to each other, we can factor the exponentials. We can do one sum, then the other sum, and so we end up with a product for the partition function. Instead of 2 separate particles now, we've got 2 different kinds of degrees of freedom. We've got internal degrees of freedom and these translational degrees of freedom that we were talking about earlier in this lecture. So what I've written here is now the partition function for a single particle, okay? And now I'm going to take account of the internal structure of that particle. So we've got the translational degrees of freedom here, right? And we've got the internal degrees of freedom. And I'm just going to leave this, and Schroeder does the same thing in the book. I'm just going to leave this as the internal partition function. Okay? This can include rotational structure, vibrational, and so forth. If it's rotation and vibration, you've already done homework problems looking at how we construct the partition function for those internal degrees of freedom. Okay. That goes along with what I said before about this sort of sneaking quantum mechanics in, right? We knew the rotational particle spectrum, or at least I told you what it was. Knew the vibrational particle spectrum. This was the harmonic oscillator, which you should have seen in quantum. Okay. If we bring those discrete spectra over, we can treat them with statistical mechanics. And then I'm just going to say L cubed is V, just in case we have sort of a funny shaped box. Okay. So the volume over the thermal de Broglie wavelength cubed times the internal state partition function. Okay. And we're again going to use this sort of factorization property of the partition function. If I have this gas molecule here and this gas molecule here, they're independent of each other, right? They're not close enough to be having some kind of interference. They're much further apart than their thermal de Broglie wavelengths, so I can just factorize the partition function. If I want to know the partition function for an n particle gas, I just take the 1 particle partition function, raise it to the nth power, and as we talked about 2 lectures ago, I need to account for the indistinguishability of those particles, and the rough way to do that is just this 1 over n factorial out front. Okay. So this is our total partition function for an n particle gas, and I'm just going to take this large factorial and treat it in the Stirling approximation, right? So this is going to say n factorial would be n over e raised to the n. I'm going to ignore the square root of 2 pi n part. We just need the biggest part of the n factorial's behavior. This would be n over e to the n. It's 1 over the factorial, so we've got e over n raised to the n. Okay? So now we've got this sort of single particle looking thing, but there's an n inside, all raised to the nth power. And I've just circled here. Again, we have the phase space density showing up. In this case, again, the partition function, 1 over the phase space density raised to the n power. Now that we know the form of the partition function, we can use it to calculate, again, a lot of interesting things. Let's start with the energy. Okay? So the average energy of the gas, or the internal energy of the gas, minus d by d beta of the log of the partition function. And now let's have that partition function here. So the log of the partition function will just drop an n out front. So we've got minus n times the derivative of, and the logarithm of all this stuff inside, right? We can just break it out. A log of a product is the sum of the logs. So we've got the log of the E, got the log of the volume, the log of this internal partition function, minus log n, minus log of the thermal de Broglie wavelength cubed. I'm going to pull out the cubed and the square root that lives on the thermal de Broglie wavelength, so minus 3/2 times the log of all these guys. So h squared over kt, I'm going to write it as beta, h squared beta over 2 pi m. Now we need to take this derivative, but hey, look, log of e is a constant, log of v is a constant. This could have some betas in it, so we're going to just sort of leave it alone, bring it down, just leave it as the derivative of the log. Log of n, no beta dependence. Aha, beta dependence here. Great. So when we take this derivative, we're going to get something that shouldn't be too surprising, which is to say the internal energy is going to look like 3/2 kt, right? 3 over 2 beta is 3/2 kt times n. Okay. So this part should look as you expect. Again, we bring down the internal state partition function, but look, minus dd beta log z internal is just the average energy of the internal degrees of freedom of a molecule times n. So our energy, we've got the translational bit that we expect from equipartition, and we've got this internal state energy. Okay, we can also calculate the free energy. Right? So we'll calculate the Helmholtz free energy because that's easy. It's just minus 1 over beta times the log. Right? So always keep in mind this relation. The internal energy is minus dd beta of the log. The Helmholtz free energy is minus 1 over beta of the log. Okay. So again, we know the partition function. We know the log of the partition function from before, right? This again kicks out an n. So we've got minus n over beta. And all of this stuff from the log of the partition function comes down, but we don't take its derivative this time. Well, what do we have? We have log of E is 1. Got log of the volume, log of the internal partition function, right? Again, these all come down. Great. So that's our free energy. I haven't done anything more to try to like reduce this or make this look nice because that's not my final goal, is the Helmholtz free energy, right? My final goal is to give you the chemical potential of the ideal gas. Again, I sort of gave it to you for free in the last lecture. Here we're going to calculate it. So the chemical potential is the derivative of the free energy with respect to number. And I should maybe not be so cavalier about this. You guys have done a lot of taking derivatives at fixed this, fixed that in 358. But we talked about in the last lecture, one way to think of chemical potential, it's the derivative of the energy with respect to number. So why didn't I take the derivative up here of the energy? It's the derivative of energy with respect to number at fixed entropy. Okay, fixed entropy and volume. The volume we can keep fixed. Fixed entropy is hard. This is not in terms of entropy. So if we wanted to get the chemical potential from the energy, we also need an expression for the entropy, and then we need to make substitutions so that we can rewrite this in terms of entropy. I don't want to do that. Helmholtz free energy, on the other hand, we're taking the derivative here at constant volume and temperature, right? Helmholtz free energy we get from transforming the Legendre transform on the energy. It gives us the free energy. The free energy, we've swapped our variables from S to T. And this is good. This is what we want. So now, right, things are written in terms of beta, which is T, and the volume. So we can hold those fixed when we take the derivative. Okay. So that's where we want to go to find the chemical potential. So chemical potential is, again, derivative of the Helmholtz free energy with respect to number, and implicitly out here at constant V and T. So let's start taking some derivatives. We've got, this is our free energy. We've got an N out front. So one part is just going to be take away the N, minus 1 over beta, times everything in the brackets. Everything in the brackets comes along. Second part should be this times the derivative of everything in the brackets, but that doesn't depend on N, that doesn't depend on N, that doesn't depend on N. I said that slowly, but think about it. What we did up above was the partition function for the internal degrees of freedom of a single particle, and then it went inside that raised to the n power, right? So because all that's left is just the log of z int, that doesn't depend on n anymore. Okay, this guy depends on n. Last part doesn't depend on n, so the only independence in here is a minus log n. That derivative gives us a 1 over n times the n beta out front, right? So this is going to be, there's a mistake here. That should be a plus, not in orange. Oh, this is gonna get bad real quick. That's a plus because, right, I've got minus log n, minus n over beta, minus minus, this makes us a plus beta, which is why these things cancel. Okay, good. So we've got 1 times negative beta. We've got a plus beta. Those go away. And so I'm going to rewrite this now as minus 1 over beta. And instead of having this mess of log plus log, push all of them together into a product. So this is log of V over N, thermal de Broglie wavelength cubed, times the internal state partition function. And what I've written here is what you get if you have an atomic gas, right? Because for an atomic gas, the only internal structure that we're going to be thinking about is the electronic excitations, which take place at extremely high energy. So for an atomic gas, we're just going to ignore this internal partition function, right? We're going to say there's only one state. So the partition function is 1. And if we do that, then the chemical potential just becomes kT times the log of the phase space density, right? Because this is 1 over our phase space density. We bring the minus sign in, that flips it to be just d, and of course 1 over beta is kT. So again, the phase space density pops up and is important. That's the chemical potential for an ideal gas. The only other thing I want to say is just if you look, the chemical potential, in some sense, in the future, we're going to use that to control the number of particles. Okay? And we're going to be able to do that because the chemical potential isn't a constant. It depends on the number. So for an ideal gas, the chemical potential depends on the logarithm of the number. Okay? So that's a theme that's going to come back in future lectures.